This video is about the basics of predicting with regression models. We saw regression models for inference in some previous lectures, but it turns out that they can also be a surprisingly useful tool for a first-pass prediction function as well. So here's some key ideas. First, we're going to just use standard regression models, whether with the LM or GLM function, to build a model that we're going to use to predict. The basic idea is that when you get a new sample that you want to be able to predict an outcome for, you just substitute in the values for the covariates, multiply them by the coefficients, and you get a prediction for the new value of the outcome. So it's a pretty simple idea, really. It's very useful when the linear model is nearly correct, but it can be a little bit difficult when the model isn't quite correct. So the pros of this approach are that it's easy to implement, it's pretty easy to interpret, and it's also relatively easy to get measures of confidence or variance about our predictions. But the problem is that it often has poor performance in nonlinear settings. So the example that we're going to be using to illustrate these regression models is Old Faithful eruptions. So Old Faithful is a geyser that is in Yellowstone National Park, which is near where I grew up in Idaho. So this is a very beautiful picture of the Yellowstone and the geyser, the Old Faithful geyser. And so what we have actually are data on the eruptions of this geyser, and we have both the waiting time and the duration of the eruption. So what we can do is we take this data set and we break it up into a training sample and a test sample. And the way that I do that is I just randomly sample a sample of about size 1/2 from the data set. You can choose different sizes for your training set and test sets. It's very common, for example, to choose training set sizes of 2/3 of the data and test set sizes of 1/3. But in this case, we have sort of a large number of samples, so 1/2 and 1/2 will work okay. So then what I do is I take that data and I plot it like this, and I can see that if you look at the waiting time on the x-axis and the duration on the y-axis, it does appear that there's sort of a linear trend relating these two variables. There might also be something else going on. As you can see, there's sort of a cluster down here and a cluster up there, but in this case we actually only have one variable that we can use to predict. So what we can do is we can fit a linear model. So what we're going to basically do is say we're going to relate eruption duration to a baseline level plus the change in eruption duration given a 1-unit change in waiting time. And we can fit that model, plus an error term, which represents everything that we haven't measured, in particular maybe that clumpiness that you saw in the variable. And so what we can do is we can fit this with a linear model function in R. And if we do that, we can actually get estimates and standard errors, and we can go ahead and perform inference just like we would previously, for example, showing that these standard errors are very, very small compared to this estimate. And so you can see that this is a very highly significant association between, statistically significant association between eruption duration and waiting time. So if we plot the model fit from that linear model, it's just a straight line, remember? So if we go to a specific waiting time, the duration time that we have for that fit is related to by this linear line here. And so what we can see is that a way that we could predict is we could just say whatever our waiting time is, we could just go up to the line and then predict the duration time from the value that you would get from the line. And in fact, that's exactly how it works. So basically the predicted value of the duration is just equal to our estimated intercept plus our estimated slope term times the waiting time. And so what you can actually calculate that directly by getting the coefficients of the model, multiplying the second coefficient by whatever waiting time you want to predict. It's in this case, say 80. And we get an estimate for the eruption duration. You can also use the predict function in R to do the same thing. So the way that you do that, you have to pass the predict function your original LM object and also a data frame that has values for the variables that you would like to predict. So for example, in this case, we have this waiting variable. So we need to set values of the waiting variable we'd like to predict for. In this case, I just set one value, 80. It would also be possible to set a data frame where waiting was equal to a long vector of values, each of which you wanted one prediction for. Then you can pass those to the predict function, and you get a prediction out that's going to be equivalent to just taking the intercept term and adding the slope term times the waiting times that we've included in our model. So an important point here is that the name of these variables in this data frame has to match exactly the names of the variable you used when you were fitting the LM function, otherwise you'll get an error. So if I wanted to plot the predictions, I could plot them for both the training and the test set. So for example, here on the left are the training set points. So this was the random subset that I used to fit the model. And so we have waiting time versus duration on the y-axis. And the fitted line is this black line right here. And so then you could also do the exact same thing, but here I'm plotting for the test set, the waiting time versus the duration. And what I have here are the predicted values. For every value that I get in the in the test set, I can actually plot the predicted value. And you can see that this looks a lot like the linear regression line that would go through these points. It's sort of not surprising here because we've taken a random subsampling, and so the pattern is about the same in the training and the test set. But you can see that this doesn't quite match quite as nicely through the middle of the cloud of points here because it actually wasn't built on this test set. It was built on the training set over here. So it's not the exact regression line that you would get if you built a regression on the test set. And you can see that in the errors. So here what I'm doing is I'm calculating this root mean squared error. So what that is I take the fitted value and I subtract the value of the actual eruption duration. And then so that creates a vector where the vector has the differences between each specific fitted value and each specific eruption duration. Then I square them and add them up. That's the sum of squared errors. So that looks very similar to the things that we use to estimate variance for regression models and that we were trying to minimize when we were doing least squares. And then you take the square root because you would like this to be on the same scale as the errors that you get. You would like the estimate of our error rate to be on the same scale as the actual measurements themselves. So since we've squared the differences here, we have to take the square root in order to get back to the same scale. And so you can see that the root mean square error here is 5.713. That's on the training set. Then on the test set, if you do the same thing, we're now going to use the predicted values from the LM on the test set, and we're going to subtract the actual values, which we know in this case of the test set data points, and we can calculate the root mean squared error on the test set, and it turns out to be slightly higher, 5.827. So in general, when you build a model on a training set and then test it on a testing set, the test set accuracy will be slightly larger, test set error will be slightly larger than the training set error. An advantage of using regression models for prediction is that you can calculate what's called prediction intervals. So here again I've plotted the waiting time versus the eruption duration. And so again I've also plotted the line that's the regression line that we estimate for this data set. So this is the line estimated from the training set, and these are actually the test set values. And so suppose I wanted to know how likely, or what's the likely region in which the test set values are going to fall. What I could do is calculate what's called a prediction interval, and that's what I've plotted in these red lines here. In this case, it's a 95% prediction interval. So our goal here is such that at each particular point, the probability that a future observation will fall within these red lines is 95%. So you can see that a very small number of the points actually fall outside of these prediction intervals. An important point to note here is that the prediction intervals sort of assume that you have data that are normally distributed, in other words, data that looks like clouds like this. So in this case, it captures very well, the prediction interval captures very well the data points. But if you saw data that was highly nonlinear, had some strange patterns in it, the predictive intervals wouldn't necessarily have the stated probability of containing most of the points in future samples. So I'm also going to show you an example with binary data. So this is an example of Baltimore Ravens data again. So these are the wins and losses that the Baltimore Ravens had in this last season when they won the Super Bowl. And so what we can do is, again, download the Ravens data and look at it. And we have a binary outcome here. The Ravens, whether they won or not, it's equal to 1 if they won and 0 if they lost. And then we have some variables that include the Ravens score and the opponent's score and so forth. And so one thing that we could do is we could, just like I explained for inference, we could treat the Raven win variable as a quantitative variable and fit a linear regression model and try to predict it based on, say, the Raven score. But a better choice would be to use a logistic regression model where we're going to model the logit of the expected value of the Ravens win variable given the Ravens score variable. In other words, the logit of the probability that the Ravens win equal to a linear function here of the Ravens score. And so we can fit that model just like we talked about when we talked about binary regression. We could fit that with the GLM function where we set the family to be equal to binomial. And then we tell it that we're fitting the model using the Ravens data. And so if I make box plots then of the predicted values from this GLM, so now I'm just predicting the values from the GLM based on the training set itself. I haven't split the data into training and test. In this case, there aren't very many samples, so I'm just illustrating how we would fit the prediction models. You would obviously need to do a training and test set if you were going to do this correctly. So if I do a box plot of the predicted values from the GLM, when I do predict of GLM here, and I don't actually include a data set, a new data set to test on, it just predicts values for the actual observations in the training set. And so if I look at the predicted values in the training set versus Raven win, you can see that those values are lower for the cases where the Ravens lost and higher for the cases where the Ravens won, but they overlap each other. It's also strange because these values actually are not just between 0 and 1 like you would expect from the fitted values from a binary regression model, and that's because these values are on the linear scale. They're actually on the scale of beta 0 hat plus beta 1 hat times the Ravens score. If you want to see them on the scale of the probabilities themselves, so if you want to look at the estimated probability that the Ravens are going to win, or the predicted probability that the Ravens are going to win each game, you need to tell the prediction function to return type equals response. So if I do that, then you can see that now the values are between 0 and 1. And again, there's a difference between the two cases, but it's actually not as dramatic a difference as you'd expect. In particular, there's no place you could draw a horizontal line and completely separate the probabilities that you're going to win from the wins and the losses. So you can't get a perfect prediction with just this one predictive variable, the Ravens score. So the output of that regression model is a probability that the Ravens are going to win. And the goal is to actually be able to predict whether the Ravens will win or not, so that's a binary variable. So we needed to convert the probabilities into zeros and ones, 1 if the Ravens are going to win and 0 if they're not. So one way that we can do that is by choosing a cutoff. So if the probability is high enough, we'll predict that the Ravens are going to win. You could just use 0.5 as a cutoff, and that's a very common cutoff, but it's not always the best one, depending on the regression model. And as we'll see here, the best one is actually not 0.5. So what we can do is calculate a series of cutoffs between 0 and 1. That's what I'm doing with this sequence here. And then what I'm doing is I'm looping over all possible values of that cutoff. And what I'm going to do is I'm going to calculate the prediction with type equal response. So that calculates the probability that the Ravens are going to win. And I look if it's bigger than the cutoff. And then I calculate the number of times that that is not equal to the value of the Ravens win. So this is the number of errors that we're making. So what I do is I calculate the sum of the total number of errors that we make for each value of the cutoff. And then I plot the cutoff versus the total number of errors that I made. So what you can see here is that you start off making about 6 errors, and then it goes up a little bit, and then down, and actually the cutoff of about 0.7, you get the smallest number of errors. You get about 5 errors, and then it goes back up again as you increase the cutoff again. And so it turns out that 0.5 is actually not the best cutoff. It will not give you the fewest number of errors in this particular case. It's actually a number that's slightly higher. Now I did this analysis entirely using the whole training set. Of course, in practice, we know that we have to use cross-validation to be able to estimate what the error rate would be in a new data set. So the way that this would work is you would actually build the predictive model in the subset that you used for training in cross-validation. Then you would evaluate the number of errors in the held-out data set that was the sub-training set that was corresponding to a test set. And then you would add up those errors and make this similar sort of plot, rather than just calculating the re-substitution error rate. So here I'm going to give you an example of how you can use cross-validation to compare two different models. So the two different models I'm going to be fitting are first the logistic regression model, where I fit GLM relating the Ravens win 0 or 1 variable to the Ravens score, and I set family equals binomial. The other model that I'm using is also relating the Raven win to the Raven score, but here I say family equals Gaussian. This is equivalent to just fitting a linear model relating the Raven win to the Raven score, the same model you would fit if this was a quantitative outcome. Then what I'm going to do is define an error measure. In this case, the error measure that I'm going to have is going to be the following. If my prediction is greater than 0.5 away from the actual value of whether you won or not, in absolute value, I'm going to call that an error. And then I'm just going to average those errors over all possible values that I'm going to predict. So, for example, if the Ravens win, then win is equal to 1. So if my prediction is greater than 1.5 or less than 0.5, I'm going to call that an error. Alternatively, if the Ravens did not win, so the win is equal to 0, if I predict a value greater than 0.5 or less than minus 0.5, I'm going to call that an error as well. So then what I can do is use the cv.glm function, which is in the boot package. I pass it the data set that I'm using and the GLM function that I want to evaluate, and then I tell it the number of folds to perform. So in this case, I tell it to perform 3-fold cross-validation. So I calculate this for each of the 2 different models, and then I can look at the delta term to see what the cost I get for each different model. So in this case, GLM1, which is the logistic regression model, actually has slightly lower cost for both of the different folds than the GLM, which uses the Gaussian model, which fits just a linear model relating the win to the score. So that actually has a slightly worse prediction. So in this case, using a binary outcome and logistic regression seems to work a little bit better. So you could do this in general with multiple GLMs by calculating the cross-validation scores for each of the different GLMs and comparing them. So some notes and further reading. Regression models with multiple covariates can be included. Here I've only included 1 covariate in the prediction, but you can include as many as you'd like. You can also include smoothed versions of variables, which we're going to be talking about next week in the lectures on smoothing. It's often useful to use linear regression in combination with other different prediction models, particularly when we're doing model blending, which we'll also talk about next week. 2 resources that are useful for looking at prediction with regression models are Elements of Statistical Learning and Modern Applied Statistics with S.